You should have watched the printf and scanf videos by now, so I thought we'd take a look at them in an actual program or two. I've got a program started with a heading comment that has my name, the date, and a short description of the program. I've also defined a few variables that we're going to mess around with. Now, the one that might seem strange is the string on line 19, but I'm going to be using that so you can see how field width affects spacing. Starting on line 21, I'm printing out that string, and I'm also printing out the int1 variable 4 different times. Line 22 doesn't have a field width specified, but lines 23 through 25 do have different field widths. Before I run this program, pause the video and think about what the output should look like. Then start the video again and see if you were right. Let's run it and look at the display. The first 67 comes from line 22, where there is no field width specified. Not a big shock here, it just prints out the 67 and takes up 2 spaces. The next 67 comes from line 23, and it takes up 5 spaces. 2 of those are for the 67, and 3 spaces are used for padding, so that it'll take up 5 spaces. The yellow lines will help you see the lineup of the spacing. Compare this to the field width in the printf statement. The next 67 comes from line 24 and takes up 10 spaces, 2 for the 67 and 8 as padding. Again, compare it to the printf statement on line 24. Finally, the last 67 comes from line 25. That one has a field width of 20, and notice how many spaces it takes up. Now, let's do something similar with floats. Line 22 has no field width, but lines 23, 24, and 25 do. Once more, before I run the program, think about what the output's going to look like. You ready? Let's take a look. We're printing the float variable 4 different times. The first time, there's no field width specified. What happened? The value printed took up 9 spaces. Now remember, the decimal point counts as one of those spaces. Another thing to remember is that unless you tell the printf how many decimal places you want, it's going to give you 6. The variable was defined as 34.81236, but look at the display. It prints 34.812359. Not the same. This tells you that a float variable doesn't have very many digits of precision. More about that in a minute. The second printf specified 9 spaces, but the output looks identical to the first one on line 22. How come? The answer is the display was going to take up 9 spaces anyway, so specifying 9 had no effect. In fact, I could have specified 9 or any number less than 9, and it would look just the same. But when we get to the third printf on line 24, that one specifies 10 spaces, and we can see that now a space appears on the left-hand side as padding. It does that so that the display of this number will take up a minimum of 10 spaces. And last, the printf on line 25 takes up 20 spaces because of the field width in that printf. All right, let's add some precision specifiers. Line 22 says take up a field width of 10 spaces, including 2 decimal places. Line 23 says take a minimum of 3 spaces, including 8 decimal places. Line 24 says take up a minimum of 15 spaces, including 4 decimal places. And line 25 says there is no minimum field width. Still, we want 10 decimal places. Let's see what it looks like. Ask yourself, does the 34.81 take up a minimum of 10 spaces, including 2 decimal places? How about the next line? Does it take up at least 3 spaces and have 8 decimal places? The next one, does it take up a minimum of 15 spaces with 4 decimal places? Finally, the last one, does it have 10 decimal places? Look over these until you see for yourself why the output matches each one of those printf statements. After you've done some reading, you might be wondering, well, what's the difference between a float and a double? They can both have decimal places. The short answer is a double has more digits of precision. Here, look on lines 15 and 16. I'm declaring a float and a double, and I define them to have identical values. Then on lines 22 and 23, I'm printing those values each time with 8 decimal places. Which one's going to be more accurate? The float variable appears to be accurate to about 7 digits. Then after that, not so much. But the double is accurate to 10 digits. And if you mess around with doubles, you'll find out that they're usually accurate to about 15 digits. So which one you use in your program depends on how much precision your program needs. And before we leave the topic of field width, I want to show you that field width works with strings also. So line 22 says print the string, but doesn't specify a field width, which means the string will print taking up all the spaces that it needs. And then line 23 says to take up a minimum of 5 spaces. Since the string Jumanji needs 7 spaces, will there be a difference on the screen between the output from lines 22 and 23? Look at line 24. It says take up a minimum of 25 spaces to print the string. Let's run this program. Here's the output. Did it match the printf statements? If you can't tell, go back and read about the printf statement again. Now look at lines 21, 22, and 23. Guess what the output's going to be? Here it is. Were you right? If this output looks like random junk, let's add some color coding. Everything that just printed was exactly what the printf statements demanded, but all of the output is on the same line. This code is missing the end-of-line characters, also known as newline characters, so let's go back and add those. Here are the same printf statements, but each format string says, after printing, go to the next line before printing the next data. Here's that output. And we don't need color coding to tell us that this output is correct. Any place you put a newline character in the format string, the display will go to the next line before printing out what follows the newline character. So now look at lines 21, 22, and 23. What will the output be? Were you right? Make sure that you see each newline character sent the display to a new line. If you're new to programming, then I'd like to give you some hints about how to translate from the specifications of a program to the actual code to make the program work. Here's an example. Read the question and look at the form the output should be in. This output will be a single printf statement. Ask yourself, where will the placeholders go for the 3 floats being displayed? I'm going to put circles around the placeholder locations. And I'm going to arbitrarily call the variables n1, n2, and n3 for this example, but you could sure name them whatever you want to. Now we'll go back and write the program based on the specifications. First, define some variables. Then prompt the user for the values and get the user's input using the scanf function. Remember, for scanf, you need line 8 in your program. Each scanf function says that it's going to get input, and then it specifies the address of the variable where that input will be stored. Now I'm just going to copy-paste the form of the output. Then I'll change that into a printf statement and put the placeholders and variable lists where they go. There's no need in this problem to specify any field widths, but I do need to make sure that all the variables display with 4 decimal places. When we look at the display, we can see that we met all the specifications. Let's try another one. Once again, read the specifications of the program. This time, there are going to be two printf statements, and we need to decide where the placeholders go again. Then, I'm going to define some variables. Next, I'll prompt the user for the number of lottery tickets. After that, we'll get their input on line 18. This line of code says we're storing the input at the address of the tickets variable. In a similar fashion, we're going to prompt the user for their name. Here we'll be using the fgets function since we're getting string input. The first argument is the string of where we want to store the input, and the second argument is the maximum number of characters we're going to allow the user to type. The third argument says the input is coming from standard in, which is the keyboard. Now let's set up how the output's going to be displayed. Once again, I'll copy-paste what I want the output to look like, then I'll fill in where the placeholders and the variable lists go. Got a problem. When I run the program, it prints the prompt for the number of lottery tickets and allows me to enter a number. Here I entered 12. But then immediately after printing the prompt for my name, it doesn't even let me type in the string. It skips right to the output, and the output doesn't show anything for the name variable. Where's the name? When I go back to the reading, it tells me that if string input comes after number input, I have to add the getC function, which is what I'm doing on line 19. We'll run it again. Okay, I'm getting closer because now the program allows me to enter a name and prints the name out. Now the problem is that it's printing an extra blank line. How come? Oh yeah, I forgot to remove the newline character from the name variable. So I'll read one more time, and I'll add a string toke function on line 22. Now to use the string toke function, I've got to include the string library toward the top of my program. Now when I run my program, it lets me enter all of the input and displays the output in the correct form. Let me point out something. I'm separating the part where I get the input from the part where I display the output. A lot of beginning programmers don't realize that these are two different things, and some of them think that the prompt and the user input is actually the output. Nope, watch out for that. The output comes after you get the input. Okay, that's it for this video. I hope that seeing the input and output functions in action will help you make more sense of all this. If you've got a question, please get with me. And thanks again for watching.